Now that you have trained your logistic regression classifier, we are going to show you how you can test it. To do so, you would start by having xval, yval and theta as inputs. These xval and yval are different data points that were not used during your training phase. And theta is the weight vector that you have already learned during your training. As an example, let's imagine we have xval as a matrix of size m by n. In this example, m is 5 and n is 3. That is 5 data points with 3 predictor features. Then, yval are the targets of such data points. As an example, we'll use a vector of shape 5 by 1. Finally, the learned weights will be a vector conformable with xval. That is, it should have as much elements as predictor variables in our dataset. Now, we will use these inputs to assess how well our logistic regression performs. In order to do that, we will need to compute the regression over the input xval using theta. For this, we will multiply xval times theta and apply the sigmoid function to it. Xval times theta will give us a linear combination of our predictor variables. In our example, it would mean multiplying the vectors xval and theta using the dot product. This will result in a column vector with m elements. Remember, in this example, m is equal to 5. The sigmoid function is computed as follows. Given an input x, it is computed as the division of 1 by 1 plus e to the power of minus x. This formula will guarantee that the output of our logistic regressor is greater or equal to 0, but lower or equal to 1. Applying the sigmoid function to every element of the product will give us a vector we will call h. Having computed h, we can proceed to get the output of our logistic regression in order to be able to evaluate it. For such matter, we will proceed to compare every element in h with 0.5 and assigning a 1 for elements that are greater or equal to that value, and 0 otherwise. Let's have a look at an example now. Imagine the output of our previous computation is this vector h. Now, we can compare every element in it with 0.5 to get a classification vector that we will call ypred. Let's now have a look at how this vector will be populated. The first element in h, 0.9, is compared with 0.5 and, as it is greater than it, ypred will contain a 1 in the first position. Then, we can use the same reasoning for the second element, which, as it is smaller than 0.5, will result in ypred having a 0 in the second position. And continuing in that manner, we will end up with a ypred that looks like this. Now that we have computed ypred, we can compare the output of our classifier with yval, our true labels. In order to do that, we will compute the accuracy of our model. Accuracy is a metric that represents the percentage of elements correctly classified by a classifier model. For calculating the percentage, or proportion, we need to compute an average. That is being represented by the sum over m elements and the division over m on the left. The right part represents the comparison, element by element, of ypred and yval. In the case they are equal, the comparison will yield a 1. Otherwise, it will yield a 0. Let's continue with our example. Imagine we are presented with a yval as this one. Now, we will compare ypred and yval element by element. and we will get a resulting vector of size m, in this case 5. Let's have a look now at the first two elements. They are 1 in both cases, hence they are equal. This will result in having a 1 in the resulting vector. This also means that our logistic regression correctly classified the first element. We can do the same reasoning for the second element in ypred and yval, and as they are both 0, we will put a 1 in the result. In the third case, we have a difference. That is, our classifier prediction differs from the ground truth. So, we put a 0. And we can continue to populate the vector in that manner. Now, we can compute the average to get the percentage of times our predictor was correct. In other words, to get the accuracy. In this case, the sum of our vector is 3 and we divide it by 5. Hence, our accuracy is 3/5, that is 0.6. If we read it as a percentage, we can say that our logistic regressor correctly classified the 60% of the validation data. With this info, we can go back to the training phase and tune our hyperparameters. For example, we can use it to change the step size alpha or k, which is the number of iterations, and so forth.